Okay, let's get started. It looks like everybody's trying to help each other out, which is great. Yeah. Huh? Yeah. There's a Zoom link ID on the syllabus. Yeah, there's a Zoom meeting ID on the syllabus. It's the same ID for every lecture. Okay. So it sounds like there might be a few questions on the project before we get started, which is fine. I did want to use part of this session for Q&A on the project anyway. So let's go. What's going on? Well, don't everybody start talking at once.
These things. Okay, so page has lots of pages, but lots of different things. Like only one of those namespaces are pages, right? It has like 15 or 20, or I'd say I think it's like 43 different types of different names.
So an article is a type of page.
And we are, oh, so that 001, maybe you can read one.
That was namespace 0, I think, was an article.
Okay. When you want us to have, when you say we want pages that link to each other, you only want namespace 0 that links to each other?
No, all pages.
Any.
You don't have to do any namespace filtering, all pages of all types.
So for every letter in page, I can have multiple letter names that you can discuss rather than the name.
Yes.
Okay. I don't understand from page names to these targets.
Okay.
Like, your page, do I have any pictures? Do I have any pictures? Why do I have this? If it's a one-to-one, why do I have to?
If you're asking me why it's structured and the way it's structured, I can't answer that because that was Wikipedia's decision, which seems odd to me. But I can tell you what it means. So the page links table, if we look at actually I didn't load the page links table. So the page links table should have the source ID of the page with the link, and it should have the ID of the link target. The link target ID is not the same as the page ID. That is the link target. So link target ID is the ID of a row in the link target table. Now, you can have multiple rows in the page links table that refer to the same link target.
Okay, so it many pages to one link target.
Yes. There is one entry in the link target table for every page that is linked to by another page. At least there should be. We should check if that's true, because Wikipedia's data set, as we discussed previously, is kind of garbage. And so they don't exactly have great consistency. For example, in the redirect table, there are actually cycles in the redirect table. I'm not expecting you all to handle those because those are annoying. Maybe I'll make a version 2 of this project where you have to handle the cycles, but that would be me. So I'm not going to do. Department chair said I had to be nice to you, so don't worry, I'm doing with reading to you. So we have this page, and this page redirects to this other page. But oh, this page also redirects back to this page. So we have a meaningless cycle where we don't actually have a page. How lovely. And there are like 400 examples of this in the Wikipedia data set. I don't expect you to handle this. Just do one redirect and you can pretend that all the redirects are equal. Because in real life, you either ignore it like we're gonna do here, or you have to figure out some rules on how to handle it, right? Which is where, oh, if it redirects to a page which itself redirects to something else, then you have to figure out if this page actually redirects to this page or if it's by itself. So you basically have to figure out if every subgraph containing all these redirects is acyclic, which is irritating. And I didn't feel like doing that, so I don't think you'd feel like doing that either.
So if I want, if my pages main target is managed one, what about my new target page?
What about your link target to page?
Link target, I mean, my link target table is giving the page which the title.
Yes. Link target should link to 0 or 1 pages. A link target doesn't have to link to a page. It can also link to a file or something else on Wikipedia. So not every link target is page. And not every page has a link target.
Actually, a page that has one link target.
I believe not, but given that Wikipedia's data set is kind of crap, it probably does. We should actually check. Who wants to check? Wouldn't that be fun? Unless we have somebody else who has a question. Do we want to find out? I think we do.
I see that I can notice before it can make something like my doors know yeah. I didn't know because I didn't think it in the new people that is or my something.
So the thing is that theoretically, every page only has one link target. Theoretically. We're going to find out if that's true. So link target has a title and a namespace. So if we were to write a piece of code that finds out whether or not these things are unique, how would we write it? Oh, I have this alias T, which is literally just spark.table, and it refers to a global temporary view. It's shorthand. Link target. Okay, so if we were to write a query to find out if there are any title namespace combinations that are repeated, which is what we would be looking for, we want to figure out if every title namespace combination is unique in link target. How do we do that? So we want to find out. Here's what the Wikipedia documentation says: is that every entry in link target refers to a unique page. So no two rows in link target should refer to the same entity. Now, based on the title and the namespace, every combination of title and namespace should be unique. We want to check if that's actually true, because in data sets like these, you can't take facts like that for granted. So how would we write a piece of code to check whether that's true or not? We could group by title and namespace. Okay, then what do we do? Well, we don't need to count the distinct. We just have to count how many times they occur. Yeah. Frequency. And then so what we also want to do is most of these things are probably legit. So we want to filter out every row where frequency is equal to, we want it to be not equal to 1. So every time we have a frequency of greater than 1, every time a title namespace combination occurs more than once, we want to know about it. So we're going to do that filter, and we're going to save the result. Link target keys. All right. Let's see what we got here. And that's the thing with the projects in this class, is that they're hard to grade, is that everybody is going to figure out how to deal with this crap differently. And if I tell you exactly how to deal with it, that means I'm giving you like a perfect scaffold to the solution, which I don't want to do. Oh, look, there are 9 rows where we have a repeat. Let's see what they are. Some of them are probably, oh, okay. So we have a bunch of things that are just null in here, which actually makes a lot of sense. So in other words, this is just junk. I'm fine with that. I don't know why it's in there, but it's junk. And that's weird because theoretically, the link target title is supposed to be part of a primary key. Is it part of a primary key? No, I don't think it is. I think it's part of an index in the link target table, and the link target ID is the primary key. Odd. Hmm? Page links. Oh, this
There's a three field pulmonary ID. We only have one with it. In our data set.
from page links?
But I don't know what we do.
Well, it might be from an older version because I know the page links table only had 3 columns when I dumped it. So that might be an older version of the table. We should check on that. Oh, yep. The page link namespace and the page link title are old. Those are the only 2 other things in there. Yeah. Yeah, that's from an older version of the table. Now it only has these 3. Now, I have to write checks like this all the time. I write sanity checks like this every time I do anything with big data. And so knowing how to write these kind of ad hoc queries is really nice. So last time I wanted to show you what an undoable join looks like, and I couldn't show you because the table I would have had to use for it required at least 80% of the answer for project 1. Now, I have a data set which is 80% of the answer for project 1. You can't see the contents or the code that was used to generate it, but we will use it to try and answer some questions here. So I ran this before class because I don't want to take 15 minutes waiting for something to die in class. So what I did before class started was I tried to write the code to find the 2nd degree links that we talked about last time. So the example we went through is Arctic links to polar bear links to carnivore. And so a 2nd degree link would be between Arctic and carnivore. So Arctic goes to carnivore is the 2nd degree link. And the problem in question is we want to find all of the 2nd degree links. Now, there are plenty of reasons you would want to do this in real life. We do this in real life at count in our identity pipeline when we're trying to take data that we think is duplicated and combine it together. We need to find 2nd degree links. And one of the big restrictive factors of finding 2nd degree links is hubs. like we talked about last time. We have these particular nodes in the graph that have a lot of incoming edges and a lot of outgoing edges. And so because of that combination, the amount of second degree links generated by that one node increases quadratically as the number of edges attached to that node increases. So I tried to run this piece of code and I knew it was going to fail beforehand. And I'm not going to show you it failing now because that would take too long. It took 17 minutes to fail. Instead, we're just going to look at it. So this was executed a few minutes ago. We only got through about 4 tasks before this thing died. So if we go and look, whoa, you can close this. If we go and look at the tasks, you can see some detail. Really? I didn't cancel this job. That doesn't look right. Did I cancel the job? Did it not boom? Huh. I must not have ran it for long enough. That's interesting. Okay. So what we're going to do instead is we're going to figure out, without actually producing the rows, how many rows would this query create? So we can project that. We can count how many rows this is going to create without actually calculating the rows. Now, we went over how to do that last time. Does anyone remember how we did that? So remember what the technique for even generating these second degree links in the first place looks like. We take polar bear from both sides of this relationship. Polar bear is a destination for some of the links, and it's a source for other links. So there are a bunch of different pages on Wikipedia that link to polar bear. There are also a bunch of pages on Wikipedia that polar bear links to. And so now we want to have every possible pairing between the group of pages that link to polar bear and the group of pages that polar bear links to. So those are the pairs that we're going to be generating for every node that acts as a middleman for that path. So we can't generate this set because it's too big, but we can generate a count for how many rows this total thing would produce. So how can we do that? The first thing we need to do is we need to take everything that links to polar bear and we need to count everything that links to polar bear. So we do, and this is called the page link IDs table, by the way. So the page, did I load this? I don't know if I loaded this. I'm going to have to load this. Okay. So this is in my private workspace. It's not accessible to you, but this is what you would need for being 90% done with project 1 is a list of page links that don't go from the page ID to link target ID. This goes directly from page ID to page ID. So that's what this table is. Oh, it looks like it's already cached. Sweet. Okay. So we need to look at page link IDs. And so now we need to count the number of pages that link to polar bear. How do we do that? That's the number of links that have polar bear as a destination. right? So we need to group by the destination column. And we need to do a count or dot aggregate. I'll just call it destination count. Okay. So now we have the destination count. Now what do we do? Well, polar bear was just an example. We want it for everybody. Wait, hold on. We got somebody else raising their hand.
Going to take itself and by its sword and so do you want to find your use the like how many times other people think about things and feel out the images of where you found and how many times that things instead of you.
Yes. So exactly. So we would join on account by the source. So we would take the page link IDs and we would group by the source. So now in this count, we're figuring out how many pages does polar bear link to. So we would say aggregate count. Okay. And then our join condition would be what? Destination, and this is an inner join. Yep. All right. So now that we got these two things, so now we have the count for the number of pages that link to polar bear. And then we have the destination, which is polar bear. Then we have the source, which is also polar bear. And then we have the number of pages that polar bear links to. So we have one row with 4 columns. How do we calculate the number of rows that would be generated by the polar bear acting as the middle node in the path? So we would multiply. Actually, it would just be, yeah. So with column. Second, we're going to call it second degree generated. And that would look like multiply those two together. And so now we have a count for everything. We still don't have the total, but we'll get there. So now, second degree children, we're just going to call it that. And we'll calculate that. Now we'll find this is actually possible to calculate because we're only getting 1 row per page. So this is easy to calculate. It's very easy to calculate the number of rows that we would generate without actually calculating the rows in some cases. And this is one of those cases. So now we can project. And the reason this is important is because over time, you'll learn how to do this in your brain in the sense that you won't even have to write this. Somebody will come to you and ask, can we do this? And instantly you'll be like, no, this is why. And there are occasions where I have had somebody come to me and ask a question like, is this possible? Can we do this? And I'll say no. And then I'll take 2 days and I'll think about it. And I'll be like, it's actually possible, but only if we do something crazy. That did happen the other day. We had something that we didn't think was doable. And then I thought about it for a couple days, came up with something crazy, and it actually worked. It was kind of expensive, but it actually worked. Mm. So we're going to see if we think it's going to be worth spending that much money on the crazy thing, but it worked. Are you like working right now? This shouldn't be taking this long. Or maybe I just have a skewed sense of time. Why? Hello? Okay, they're a 9 running. Good. I thought I was losing it for a second because, and we'll talk about this later. Um, you can tell how much compute resources you have access to on this executors page, and it will tell you how many executors are running, how much memory they have access to, how many cores they're running, and such and such. And so this is useful if you want to find out if you're not making proper use of the hardware that you've allocated on the cluster. And sometimes that's really important. Okay, it's almost done. This is taking longer than I thought it would, but it is working. That's probably because this cluster actually has two smaller instances instead of one larger instance. So we have to do actual shuffling when we do the group by instead of just doing fake shuffling. All right, so this is what we got. We have, I can't even read this number, 18 million rows in this thing. So the only information this is going to have is how many rows would be generated by this node acting as a middleman. So let's see. Let's just look at a sample and see what we got here. Whoa. Oh, that's not helpful because they're all IDs. Dang it. Okay. Well, you can kind of see that this gets pretty ridiculous pretty fast. So in this page, I don't even know what this page is. You can actually just look. Key page. E equals 6, whatever that is. Let's see which one this is. Oh, it's Arnold Schwarzenegger. Okay, good to know. We come up with the most random crap in this class. It's fantastic. It never fails to make me giggle. Okay, so apparently 5,400 other pages think Arnold Schwarzenegger is relevant enough to link to him. And Arnold Schwarzenegger's page also links to 1,200 other pages for some reason. I don't know why he needs so many references, but he has that many references. Now, that amount of linkage produces, what is this? 6.6 million rows just from Arnold Schwarzenegger. What a monster. That number is almost as big as his muscles. So now we can figure out using this. All right, what's the total number of second-degree children that are generated from trying to do this query? Now, we already know it's going to be huge based on just this incredibly small sample of just enormous results. And it looks like, just by glancing at it, that this one actually has the largest number of second degree children. So I want to see what this one is. Bavaria. So it looks like Bavaria is more interesting than Arnold Schwarzenegger, according to Wikipedia. Which it might be. I don't know. I've never been. Huh? Nope. Oh, there we go. It's called homicide. Okay, I actually want to see what the Wikipedia article looks like for cult homicide because how do you only have 3 links to that? How do you only have 3 links to cult homicide? Cult homicide. Disambiguation? Yeah. So if it's a redirect, then why is it in this table? That's interesting. It must have been a redirect to another table. So that's the other thing is that sometimes redirects have redirects, and I'm not requiring that you handle that because that's stupid. We should only have one level of redirects. But this actually makes sense because if it's a redirect of a redirect, it's not going to be linked to very often, which is what we're seeing here. But that doesn't match up with how likely we think the word cult should be linked to in Wikipedia. I refuse to believe only 3 articles think cult homicide is interesting. Okay, let's sum all these up. All right, is that number even going to fit on the screen? Okay. Now, help me read this number. 1, 2, 3. Oh, okay. So it's 540 billion rows, which means that on average, how many pages do we have? Um, so on average, it means about we have we have what 8,000? We have 8,000 second-degree children generated per node or per Wikipedia article, which actually isn't that much. That's a way smaller average than I was expecting. Now,
Right, if there's a, or a gate function, it might have to be local. That logically said, if somebody reads a video artists, do you have to only count referencing the page table that are active? If your page table has access to other things, it's all about it.
well, yeah, but other kinds of pages like talk pages, they can link to all sorts of things. Um, but you're right. The pages with the largest number of links we would expect to be articles. So I also want to see what the maximum number of second degree generation we're going to see. Whoa. Okay. So the maximum number that we see is 5 billion. So one page out of the 6 million pages, one page is supplying 1% of this number. That's crazy. But you will see imbalance in these kinds of data sets all the time. This is so common. I fully expected to see this. I kind of do. So let's see. I do want to know what the page is. Um, it's going to be. Oh, wow. That is quite imbalanced. Okay. Which also should be expected now that I think about it. So, what is this page? Biography. Really?
really general.
No, what's the namespace though? The namespace isn't one. The namespace is 100. So what is that namespace? Portal? What on earth is this? Oh, portals serve as enhanced main pages for specific broad subjects, primarily for readers while encouraging them. Okay. Oh, here we go. Biography portal. There we go. I didn't even know these things called portals existed on Wikipedia. Interesting. Have you ever seen this page? I've never seen this page, but apparently it's the most linked to page on Wikipedia. Well, okay, no, it's not necessarily the most linked to page on Wikipedia. It's the page that will produce the most second degree paths on Wikipedia is this page I've never heard of or seen. That's unusual, but I think it's funny.
Does make perfect sense.
Oh yeah, it makes perfect sense, but I've just never seen it. It's kind of weird how it's so common we barely interact with it as normal users. And that's the thing. This kind of imbalance is so common. You will see it everywhere. It's absolutely everywhere. And so learning how to deal with imbalances like that is really important. I mean, the way we dealt with an account is just we deleted everything that was big. And at least for us, that was fine because a lot of the things that are big are also BS in the sense that no singular person in the world owns 100,000 credit cards. I don't care how addicted to shopping you are. You do not. That is not a thing that happened. That is somebody who stole a bunch of credit cards and used the same email.
I'm not sure something like really I like the biology page, like for somebody necessarily in the universe, that people are thinking, versus the um
No. And that's the other thing is that sometimes this graph information will reveal like extremely deep relationships between the stuff on Wikipedia, but it's not necessarily what everyday users interact with. Now, there's no reason this information can't be useful. Like when we try to find hubs like this at Count, hubs are really interesting because they almost always mean something, at least in the context of the data set that you're looking at. In this one, I don't know what everything linking to biography means. Maybe it's just that, every page that is a biography also links to portal biography, which would make a lot of sense. But then that means that biography represents a higher level concept on Wikipedia than most other articles. So there is information here, and it's deep information about the structure of Wikipedia. And that could be interesting. For us, what a lot of hubs mean is, sometimes an online store that sends us data at count, a hub might be like a default value. Instead of the empty string, they might use no email at walmart.com instead. They'll use like the string, no email at walmart.com. And that's paired with a bunch of different other things, like a bunch of different credit cards, because that's assigned to every single transaction they send us. So it looks like every transaction is using the same email if we don't know ahead of time that that email is a default value sent to us by that customer. So this information can be very interesting. Or it could also be fraudulent behavior. We have hubs that exist entirely because they are fraud and for no other reason. It's like, oh, this guy tried to buy 700,000 things using 700,000 different credit cards from this one online store, and he used the same email every time, so we caught him and we rejected all of his transactions. But it's good to know that he tried, because now we can notify the people that their credit cards have been stolen. So it's good to know. Are there any questions on things like this? Because I think this is a really interesting example of a thing that you can't calculate, but you can quantify how much you can't calculate it. If we had a larger cluster, this would actually be doable. I expected this to not really be doable, but this would be doable on a much larger cluster. Because I deal with multi-billion row clusters all the time, or multi-billion row tables all the time.
Number of rows we generate for the end, because we have all of them, but not minimum shifting and
Shuffling?
shuffling.
Not really. It's pretty much only the amount of rows at the end. But that depends on the kind of join that you do. And we'll get into this more some other week. We can maybe even talk about it now. We have enough time. Unless somebody has questions on the project that we want to go through. Because I also wanted to set aside some time for asking questions on the project. Yeah, yeah.
First of all, I did get it to work.
Good.
Are and it's a simple question, but just the schemas for the data sets that you got in the table headings are all the exact same.
Yeah, they're all the same. So you can read the Wikipedia documentation on different columns in the tables, and they should match the exact same columns from the data sets you'll find in SQL. Okay, good. Nobody has any other questions? So we're all good? Can I move up the due date? Change of plans, it's due on Friday. And then I can give you project 2 next Tuesday. Okay, we can talk about joins. I like talking about joins. This is one of my favorite topics to talk about in Spark, because where is it in performance tuning? So this is actually sort merge. Yeah. Where are the join types? Oh, there we go. Okay. So let's go through what happens when we need to do a join. When we need to do a join, we have a bunch of rows that are completely unorganized on different machines potentially. And in this cluster, they actually are on different machines, because this cluster uses 2 machines and not just one, like the previous examples that we've gone through in class. So in order to actually generate these second-degree pairs, what would we have to do? The data has to go somewhere. That's the wonderful thing about software, is that none of it's magic. So once you know how software works, you can kind of just like guess how everything works because there's only like a few logical ways to do something. Yeah. So like everything with the same join key has to go onto the same machine. So we can say that um so with this page link ID table, we're taking the source from the page link ID table and we're joining it on the destination of the page link ID table. And the reason we're doing that is because that will give us a triplet, right? So on one of these tables that we're referring to the source. So this gives us every row with the source matched up to the destination second group. So we'll take the destination from this select expression and match it up with the source from this select expression over here. And that will give us these triplets. That make sense? Okay. So the value of the join key is for this table that we're joining, because we have to pretend these are two different tables. So the value of the join key for this table is the destination. The value of the join key for this table is the source. Right? Right. Okay. So for the first table, we send everything with the same value. So every page link with that links to polar bear, we're going to send it to the same executor. We're going to send it to the same machine. And we're going to take this other table and everything with the source of polar bear, we're going to send it to that same machine. So everything with the same value of the join key from both tables gets sent to the same machine. And so that means when we wind up on the same machine, we get a collection of pages, a collection of rows that looks something like this, right? We have, let's see, what else would link to polar bear? Seal, because seals are eaten by polar bears. And what would polar bear link to? Polar bear links to, sure. Polar bear links to global warming and such and such. I don't know why this is bothering me. Okay. So we have this entire collection of things on the same machine now. But we still know that they're from two different tables. So this is going to be from the second table. These last two rows are going to be from the second table. These first two rows are going to be from the first table. And so then what we do is we need to choose our join strategy. And so when you join on a join key, there are really only two strategies. There's the hash join and the merge join. Now, for basically every application, a merge join will be better. I can't think of a reason why you would actually want to use a hash join. Merge joins are much better memory-wise. So the difference between a hash join and a merge join is, whoa. Because, polar bear is probably not the only join key that's sent to this machine, right? There are lots of other join keys that are also sent to the same machine. So what you would need to do is, as you iterate through all of the rows, as they're being received by the machine, you need to build this hash table to create the resultant join rows. So this hash table is probably going to look like, okay, we have a join key, polar bear, and this happens for every join key. If we have another join key that's like expo, because I have a marker on my desk. Now, everything with expo as a join key would also have their own entry into the hash table. So all of these are managed completely separately, and we go through it in a stream. Does that make sense? Okay. And so then what we would do is we would take the values for um we would take the values for every uh for every piece as they come in, for every row as they come in. So it would be you would have maybe a list of rows 1, and that would be a list of these pairs. We'd have a list that looks like this. Actually, I should use like actual legit Python syntax for this. So 1, and then for the other, we would have seal. Okay. So now let's say those two come in first, and we didn't get any rows from the other data set yet. So for now, rows 2 from the other side of the join is empty. For now, it's empty, but we got another one coming in. So we're streaming, and this guy came in, and now we have polar bear links to carnivore. So now, for everything that we receive, we would loop through all of the rows that we've already received in the other set, iterate over them, and generate a new row for every row that we have in the other set currently. Make sense to everybody?
Yes, but how do you know that your first set's complete?
You don't have to. Because let's say it's not complete, right? Let's say we only have seal polar bear. When let's say we only have Arctic polar bear when polar bear carnivore comes in. So we don't have seal polar bear yet. We don't know it exists. So we only produce Arctic polar bear carnivore. That's the pair that we produce as a result of the join. So then we have then right after that we have polar bear seal come. Why am I not copying properly? I am copying properly. I deleted it. Oops. Okay. So now we have seal polar bear coming in. Now what seal polar bear does is it will look at everything in the other list of rows that we already have, and it will generate a pair based on that. So we've already generated the pair for Arctic polar bear carnivore. So that's fine. Now we have to generate the pair for seal polar bear carnivore. So as this new one comes in, we can generate those pairs. Yeah. And so then, lastly, we want to generate the polar bear global warming and all the pairs associated with that. So then, when this polar bear global warming row comes in, we look at all the rows from the other side, and we generate the seal polar bear global warming pair. We also generate the Arctic polar bear global warming pair. So that's how we stream them in. So we can generate them ad hoc as they come in, and we have to maintain this hash table. So the hash table will continue growing, but it grows linearly and not quadratically, because we don't need to store every pair in the hash table. We just need to store everything individually from one side of the join and everything individually from the other side of the join. Got it? Good. Any other questions? You get hash joins? Cool. Now, I really like sort merge joins. So that is called a shuffle hash join or a hash join. And so if you want to use a shuffle hash join, you can tell it to use the shuffle hash join strategy. So you can tell Spark which kind of join to use. It doesn't guarantee that it will use that join strategy, but you can check the Spark plan to see whether or not it will actually use what you're telling it to use. It will almost always use what you tell it to use. So now merge join. Can someone venture a guess as to how a sort merge join, just based on the name, would be implemented? And in order to illustrate the concept, I think I need to create multiple join keys. So somebody give me another join key. No, we're just going to call him Arnie. So Arnie links to Terminator. I can't spell. And Terminator also links to Arnie. What's another movie that we've seen him in? Total Recall? Who's in Total Recall, right? True Lies.
State of California.
Yeah, there we go. Huh? What? Kindergarten Cop? What? I've never heard of this. Okay, Arnie links to California, but maybe California doesn't like him all that much for some reason. I don't know. And so California doesn't link to Arnie anymore. So what was it? Kindergarten Cop? So maybe Kindergarten Cop links to Arnold Schwarzenegger, but Arnie does not link to Kindergarten Cop because I've never heard of it. So that's what we're going to go with. Okay. So we have a bunch of things linking to Arnold Schwarzenegger. We have to separate this properly. Let's just copy. What's this? Okay. So we have a bunch of things linking to Arnold Schwarzenegger, and that would be on this side. And we have a bunch of things that link to Arnold Schwarzenegger, so that would be on the other side. So how a sort merge join works is, imagine you have like two lists. One list represents the first side of the join, and the other list represents the other side of the join. Now, before we can do any joining, both lists are sorted. And the reason they need to be sorted is we'll start off after they're sorted. They're both sorted by the join key. So after they're sorted, we'll go down and we'll generate every pair for everything else in the other set. So, and then we'll iterate down. So right now, our current like index pointer is on polar bear for set 1. Our index pointer is also on polar bear for set 2. And so we'll start, this is basically a double nested for loop now. So, while our index pointer is pointed at rows that have the polar bear for the join key value, we're going to generate a new row. So when we have Arctic, for Arctic, we're going to go through every row in the other set that has the same value of join key. And this is going to be simple because when we're iterating down, as soon as we hit a row in the second table, in the second part of the join that doesn't have polar bear as the value for the join key, we can stop. So it's sorted that way. So we'll start with Arctic, and then with Arctic, we will iterate down the other list of rows for the other side of the join, and we'll iterate through all of the other rows with polar bear as the join key, and we'll generate all of those pairs. And then once we're done with everything that Arctic needs to do, we'll go for seal, and then we'll iterate over the exact same row set to generate all the pairs for seal. And then now we're done. So now we move on to Arnold Schwarzenegger. So then we start off with the Terminator Arnold pair, and then with the Terminator Arnold pair, we will iterate over every row labeled Arnold in the other set of rows. And we'll continue doing this kind of lockstep all the way down until we finish. So that's a sort merge join. Does this make sense to everybody? Yes, you do. You cannot stream as you can with a shuffle hash. Almost always. It's faster for non-trivial amounts of data. And the reason I say that is because it's actually much easier to get this to fit into memory than it is to get a hash table to fit into memory. It's kind of like what we were talking about earlier, where once you deserialize something and represent it in memory, it's way more memory intensive. You can do this while serialized. You don't have to load any of this into memory in order to iterate over it. But you do have to keep the hash table in memory. And in my experience, like loading a hash table into memory is probably 4 or 5 times more memory intensive than doing it this way. And so for smaller data sets, shuffle hash would be faster because it's a hash table and you're keeping everything in memory and you could stream it and everything's wonderful. But if you can't stream it, and a lot of the time you can't because you won't have enough memory, this is going to be the faster option. Because you don't actually need to put something into memory in order to sort it, and you don't need to put something into memory in order to iterate over it. At least if it's structured like this. Because on disk, you can just store one row, one after the other. And there doesn't have to be any gaps between them. And there's no memory fragmentation because there's no pointers. It's just a series of bytes on disk. With a hash table, you know, every entry exists in its own little object, and there are gaps between all these objects. And especially in Java, it's pretty bad because in Java, every struct or every object is its own memory allocation. And so that makes things even less efficient. And so a lot of the time, it's better to use a merge join, a sort merge join, instead of a shuffle hash join, because it uses memory much more efficiently. And in fact, using a sort merge join is so much more efficient that here's another story. So telling Spark to use sort merge joins, it's better now, but in older versions, it was kind of crappy and it didn't always do what you told it to do. We had a giant aggregation with, you know, we had what, 700 million unique keys that we were aggregating over. And like joins, aggregations also have a hash aggregation and a sort aggregation, and they work in very similar ways to a join, where before you aggregate, you sort the data and then you go through it. With a hash aggregation, you have a hash table, and the values of those hash table is the aggregation state for every key. And so in this aggregation was being done in Snowflake. And I can guarantee you that Snowflake was using a hash table internally instead of sorting the data. And The reason it does this is because for certain types of aggregations, using the hash is better. This is what makes it just different from a join. And we'll talk about aggregations a little bit later. But it was using a hash aggregation, which is much less memory efficient when you have a large key set. And so I had to port it into Spark and manually sort the partitions in Spark and then do a sort aggregation that way. Now, in the earlier version, we actually had to split this aggregation up into 5 different queries and then join all the results together. But in the Spark version, where we did the sort aggregation ourselves, we only had to use one query. We didn't have to do any joining after that. So both a sort aggregation and a sort merge join are much more efficient memory-wise. And especially in the case of joins, a sort merge join is almost always the best option, especially if you have a local disk to work with. Because you're right, you can't, you have to have all of your data before you start actually producing the rows from the join. But the problem is that, you know, in the hash or in the shuffle hash join, you still have to keep everything as the new rows come in. You still have to keep everything as the new rows come in, but it's a lot less efficient because you have to store them in a hash table versus just storing them as string numbers. Does this make sense to everybody? Because this is going to be on the exam. This difference is going to be on the exam. And I know I haven't actually mentioned the exam until now, but this is when we start getting into the more theoretical aspects of Spark. And that's part of the goal of this class is I can't show you all the possible errors that you're going to go through in Spark. I can teach you how to use it on a basic level, and I can give you the theoretical knowledge. And then when you're in industry, it's your job to use this knowledge to try and figure out why something is running out of memory. Because replicating this in a classroom controlled environment in a way that doesn't cost us $20,000 is really hard. So that's what the split is going to be. The projects are going to assess your practical programming skills with Spark, and the exams are going to test your theoretical knowledge like this. So you got to know how these joins work. You have to know the difference between the two different types of joins. I want you to be able to describe to me how these joins work. When I do dot,
So like, so you could, sell the world, looking for actually like in the document. Which one would be?
oh, we can check the plan. Let's just generate this again, actually. Oh, this one doesn't join. Okay. Wait. This is 19. I have to find the right job that corresponds to that query. Hash aggregate, exchange, single partition. Sort merge join. So that one is using a sort merge join.
So we can just decide like on the private one.
Yeah. And you can tell it which one to use. So you can go like dot hint merge dot hint merge, and then that will give us how much time do we have? Yeah, that will give us our sort merge join. We can also have the other hint, shuffle hash, See what happens with that one. Int shuffle hash, shuffle hash. And let's see what the plan looks like over here. Wait. Hash aggregate exchange. This isn't all that helpful, so we need to look at the details. Is it still doing? It looks like it's still doing a sort merge join. Let's look at the physical thing. It might be because the result is already cached. So let's do a spark.catalog. Like I said, it doesn't always listen to you, or that's listening to that. So let's see if that actually cleared the cache, and see if this works. Okay. So got that. Okay. Let's look at the actual plan for this. Hash aggregate exchange. It's still doing a sort merge join. Why are you not listening to me? Okay, well, at least it's telling us which one it's doing. Huh? Yep, that's why it's just a hint. It's not listening. And then there's a third kind of join called a broadcast join. And a broadcast join is where it takes one side of the join and actually replicates it and sends it to every single node on the cluster. And then it does the join locally. So beyond the broadcast, a broadcast join doesn't actually require a shuffle at all. But as you can imagine, the broadcast join is expensive because it involves replicating the data set for as many nodes as you have. So it only works when one part of the join is really small. We're just about at time. Are there any questions on join strategies? Of what? You're talking about the Cartesian product? That's something we almost never do because it pretty much always produces a set of rows that's too big. You can do a Cartesian join. So types of join. It's called a cross join. There it is. Full join returns the Cartesian product of two relations. So that basically takes all the rows in one table and that makes a pair for every single row in this table with every other row in this table. It's a huge join. So I have never actually done this with a real data set. It's too much. But if you need it, it's there. And it has mentioned semi-joins and a bunch of other stuff, but there's not much to it. These are just set operations. That's all. Yeah, anti-join is literally just set subtract. Anti-join returns values from the left relation that has no values with the right. That's a set subtraction. That's all it is. And data frames have different methods for that. So in the data frame methods, it's not called anti-join, it's actually called subtract. But that's it. We're over time. Any other questions? All right, office hours is now. Thank you.